Hi, good day. In our past discussion, we already learned the concept of buffer solution. We learned that buffer solution is a solution of weak acid and the salt of its conjugate base, or a weak base and the salt of its conjugate acid. Also, we learned that buffer solution can resist a sudden change in pH. Now, just like other type of solution, buffer solution has its own pH. The question is, how are we going to determine the pH of a buffer solution? To answer that question, we need to go back to the topics Bronsted-Lowry acid-base mechanism and dissociation constant expression for acid. Now, this is a hypothetical equation that shows the Bronsted-Lowry acid-base definition. Here, our hypothetical acid, HA, is dissolved in water, H2O. Now, between these two, water will act as a base and HA will act as an acid. Now, as an acid, this HA will donate hydrogen to water molecule, and this water molecule will now turn to H3O positive or hydronium ion. Our base here is water, and its conjugate acid is hydronium ion. On the other hand, after its donation of hydrogen, this HA here will now turn into a negative ion. Our acid is HA, and its conjugate base is A negative. Now, to create a buffer solution, we need to combine this HA into a salt that contains a negative ion. Now, if we are going to write the dissociation constant expression for this equation, then we will have here Ka is equal to, or dissociation constant for acid is equal to the hydronium ion concentration, okay, or the molar concentration of hydronium ion, multiplied to the molar concentration of our conjugate base. In this case, our conjugate base is A negative, divided by the molar concentration of our parent acid, or our hypothetical acid, HA. Now, if you are not yet familiar with the dissociation constant expression, might as well watch my video about dissociation constant expression, and the link for that video is on the description box below. Now, if we are going to rearrange this equation and we are going to cross-multiply this molar concentration of HA here to this Ka, then we will have here HA, molar concentration of our parent acid, multiplied to Ka is equal to the molar concentration of hydronium ion multiplied to the molar concentration of our conjugate base. Okay, and by dividing both sides by A negative or conjugate base, then we will have here HA multiplied to Ka over the molar concentration of A negative, which is our conjugate base, is equal to the hydronium ion concentration, okay, and our A negative here will now be cancelled because again we divided both sides by A negative or our conjugate base. And then we will have here the hydronium ion is equal to HA, a molar concentration of HA multiplied to Ka, or the dissociation constant for acid, over the molar concentration of A negative or our conjugate base. Now, we can actually stop at this equation and use this equation to find the pH of the buffer solution. Since after we computed the hydronium ion concentration, we can actually substitute its value to this formula. pH is equal to negative logarithm of hydronium ion concentration, and that's it. We now know the pH of the buffer solution. Or we can actually continue our derivation and multiply both sides of this equation by negative logarithm, and we will have here this equation, okay, this one, which is actually multiplied to negative logarithm. Okay, and by distribution, we will have here negative logarithm of hydronium ion is equal to negative logarithm of the dissociation constant for acid minus the logarithm of the ratio of the parent acid over the conjugate base. Now, we already knew that negative logarithm of hydronium ion concentration is also pH. Okay, and the negative logarithm of the dissociation constant for acid is also pKa. And therefore, instead of saying negative logarithm of hydronium ion concentration, then we can actually say that it's just a pH. And this negative logarithm of Ka is just a pKa, okay, minus the logarithm of the ratio of our parent acid, our acid, over the molar concentration of our conjugate base. Now, by flipping this equation, that is, we are going to put this A negative here, or our conjugate base here, as a numerator, and our HA here as our denominator. By flipping this equation, then we will have here positive log instead of negative log. And the final formula for this one is pH is equal to pKa plus logarithm of the ratio of the conjugate base over the molar concentration of our parent acid. Or simply, we can actually generalize this equation into pH is equal to pKa plus logarithm of the molar concentration of base, instead of A negative, base, over the molar concentration of acid. Okay, the acid that we used in our buffer solution and the base that we used in our buffer solution. Okay, now this equation is actually widely used in chemistry, and this equation has its own name, and it is actually known as Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation was first derived by Lawrence Joseph Henderson and Carl Albert Hasselbalch. Remember the first part of our derivation, this part? This was actually derived by Henderson in 1908, and the second part of our derivation, this part with negative logarithm, was actually derived by Hasselbalch in 1917. And so we have here the Henderson-Hasselbalch equation. pH is equal to pKa plus logarithm of the molar concentration of the ratio of our base in buffer solution over the molar concentration of the acid in our buffer solution. Now, to give you an example on how we can use the Henderson-Hasselbalch equation in finding the pH of a buffer solution, let's have here the first example. Find the pH of hydrofluoric acid sodium fluoride buffer. In this case, our hydrofluoric acid is of course the acid, and sodium fluoride will be the base. A buffer that is made from 0.1 molar hydrofluoric acid and 1.2 molar sodium fluoride. The dissociation constant of hydrofluoric acid is 6.6 times 10 raised to negative 4. Okay, so for us to be able to compute the pH of our buffer solution, we are going to use the Henderson-Hasselbalch equation. Now, there are actually some values that are needed in Henderson-Hasselbalch equation. Namely, these are the pKa, the molar concentration of base, and the molar concentration of acid. Here, we have the molar concentration of base, and that is 1.2 molar. Again, sodium fluoride is our base here. We also have here the molar concentration of acid, and that is 0.1 molar. That is actually our acid here. But we don't have pKa. Instead, we have Ka. So how are we going to get the pKa from our Ka? So again, in our past discussion, we already knew that pKa is actually equal to negative logarithm of Ka. Now, by substituting the value of our Ka here, which is 6.6 times 10 raised to negative 4, to our equation pKa is equal to negative logarithm of Ka, then we will have here pKa is equal to negative logarithm of 6.6 times 10 raised to negative 4. That is our Ka, or dissociation constant for acid. And by doing this in your calculator, then we will have here pKa is equal to 3.18. Now, we can substitute this value to our Henderson-Hasselbalch equation. And let's proceed now to the Henderson-Hasselbalch equation itself. So the Henderson-Hasselbalch equation is pH is equal to pKa plus logarithm of the molar concentration of base over the molar concentration of acid. We know here that our base is sodium fluoride and its molar concentration is 1.2 molar. So we just substituted its value here. And we know that our acid here is hydrofluoric acid, and we just substituted its value, which is 0.1 molar here. Okay, and we already determined the pKa of hydrofluoric acid here, and that is 3.18. Okay, and by doing this in your calculator, then we will have here pH is equal to 4.26. Therefore, the pH of this buffer solution, which is actually made from 0.1 molar hydrofluoric acid and 1.2 molar sodium fluoride, is 4.26. Now, let's have the second example. A buffer is made from combination of 0.8 molar ammonia and 0.1 molar ammonium chloride. What is the pH of the buffer? The dissociation constant for base of ammonia is 1.8 times 10 raised to negative 5. Now, for this problem, our base is actually ammonia and our acid is ammonium chloride. Now, how did I know that ammonia is my base and ammonium chloride is my acid. I just compared their hydrogen content or contents. The one with higher hydrogen content or contents will be the acid, and the one with lower hydrogen content or contents will be the base. In this case, NH3 has 3 hydrogen and NH4 has 4 hydrogen. So this one has higher hydrogen content, therefore this one is an acid and this one is our base here. Okay, now again, there are actually 3 values that we need to have in order to use the Henderson-Hasselbalch equation in finding the pH of our buffer solution: the pKa, the molar concentration of base, and the molar concentration of acid. Here we have the molar concentration of base, and that is 0.8 molar. We also have here the molar concentration of acid, and that is 0.1 molar. Ammonium chloride again is our acid here, but we don't have pKa. And instead, we have here Kb. Okay? So, how are we going to use this Kb in order to find our pKa first? We can actually use this formula, pKb is equal to negative logarithm of Kb, to find our pKb. And after finding the pKb, we can actually subtract the value of this 1 to 14 to find our pKa. And so, by using this formula, pKb is equal to negative logarithm of Kb, then we will have here pKb is equal to negative log of 1.8 times 10 raised to negative 5, which is actually the dissociation constant for base of ammonia. So that's it. Okay? And by doing this in your calculator, then we will have here pKb is equal to 4.74. But again, that is not what we need. In Henderson-Hasselbalch equation, we need pKa. So, we can actually use this formula. Okay, pKa plus pKb is equal to 14, since we already have here the pKb. Okay, now by using this formula, pKa plus pKb is equal to 14, then we will have here pKa plus 4.74, which we already determined earlier, 4.74, is equal to 14. By transposition, then this one will become negative, and pKa is equal to 14 minus 4.74, and pKa is equal to 9.26. Now, we can substitute this value to our Henderson-Hasselbalch equation. Again, the Henderson-Hasselbalch equation is pH is equal to pKa plus logarithm of the molar concentration of base over the molar concentration of acid. In this case, the molar concentration of our base here is ammonia, is 0.8 molar. And the molar concentration of our acid here is ammonium chloride, is 0.1 molar. Now, our pKa here is 9.26. Okay? So, pH is equal to 9.26 plus logarithm of the molar concentration of base, which is 0.8 molar, divided by 0.1 molar. And by simplifying this part of the equation, 0.8 divided by 0.1 is 8. And we will have here pH is equal to 9.26 plus logarithm of 8. And by simplifying further this part of the equation, logarithm of 8, the logarithm of 8 is 0.9031. Okay, and so we will have here pH is equal to 9.26 plus 0.9031. And pH is equal to 10.16. Therefore, our buffer solution, which is made from 0.8 molar ammonia and 0.1 molar ammonium chloride, its pH is actually 10.16. Okay, so that's how we can actually use the Henderson-Hasselbalch equation in finding the pH of a buffer solution. So thank you for listening and good day.